Hey guys.
Hi, folks. So
Hey guys.
hi, Doreen.
Hello. How's it going?
Good, good. So last week we basically looked at chapter 8 and we saw about distillation. We walked through the distillation stuff. Unfortunately, we were not able to finish and we just stopped at quantization, I guess. And we said, okay, we can just, you know, finish today. And yeah, so today we're gonna look at basically the last part, which is not that uh, too much for the chapter, which is contest.
Sounds good.
Right. I think we can just get going. So last week we I think we discussed about this chapter, which is basically model compression, and we said that many ways to do compress a model because big giant models they cannot move into smaller devices, and the better solution we talk about is knowledge distillation, quantization pruning, and graph optimization with ONNX and ONNS runtime. And we saw a lot of stuff on knowledge distillation where we saw DistillBat, where we apply knowledge distillation. And today we're going to continue with this one, which is quantization. So, yeah, so basically, as we saw last week, the quantization, I mean, the model distillation, what it basically does is reduce computational and memory cost. As we can see here, what we are trying to do is here we can see here we have BART base. We can see this is a latency, and we can also see that the accuracy is somehow good, but we have a distill bar without distillation. And now here we have distillation. We can see like the latency really decreased, and now it has a good performance with but the giant model. One thing we should know is that the computational and memory cost for distillation model here we had is much, much slower than the BART base. But there are other ways to do this. Quantization take a different approach. Instead of reducing the number of computation, it basically represent with different kind of floating point uh, representations. Please, if this is my first time reading this kind of stuff, if you have anything, you can jump in and correct me. So what we are doing previously, for example, for many architectures, those big giant models, they use by default, I think, a 2-bit floating point. So quantization is a way in which basically we reduce we make the models more efficient by representing the weight with low precisions. And what we mean by low precision is that maybe instead of using 32-bit, we can use like maybe 6-bit and other representation, 8-bit and 16-bit, which are widely used. But we should know that quantization may result in low accuracy because basically because there is a kind of trade-off because quantization, we are reducing the precision. So it turns out that when you do quantization, of course, the accuracy may reduce. But what it turns out, they say that even though when you do quantization, you are doing low precision, it has been demonstrated that the accuracy that you're gonna lose is not such kind of significant, and it was while doing the quantization to actually reduce the uh, number of computations. So that is it. One of the things also they make mention Yeah, so there is something like this here. I don't actually understand if somebody understand what this they are trying to figure out. I didn't understand what this means. Yeah. If anyone understand what this from the book means. So what they said here is, okay, one good reason why transformer and this are prime candidate for quantization is the weight of activation tend to have very small values. So we know that when we do like the quantization, we are bringing these some values to small range, but it turns out that we can see that this is the weight and activations. We can see that the values here, they are very small. So they are not represented somehow kind of very large values. So it's a good candidate that we can just use quantization. So now, for example, now here, this model with this weight, we want to assign it back into 8-bit signed integer, which is from 32-bit. We can do several stuff, which for number one, we can define a scale, which is defined by finding the range and divide by the, we divide by the way we want to basically the scale, which is 8-bit sign, which is the minimum and the maximum here. We divide this, and now we can do something like this. For each weight, we divide by the scale here, we calculate and 0 point and clump them into this range. And now this is just conversion. So this is where we do here, we quantize this, all the weights here. I'm not sure why here we are using 0 point equals to 0. I don't know what the meaning of this while we assign this. So if anybody can understand. So this is just to show us how the weight are. Does anybody know why this 0 is equals to 0 is assigned? But also we can do from PyTorch, we can just import quantizer patterns. So we can, given any weight, we can just, this is a scale I made mention here, we calculate using this guy, and now 0 point and the data type. So you can see this is just the quantized weight we have. Also, if we want to do, okay, so this is also the, just showing us the quantization of the stuff. But also here, they also try to show us like how the time it takes, because using the weight without quantization and trying to find out how long it takes to, do basic calculations. So this is just the multiplication between the weight without quantize, and this is the time it takes. And now here they want to do, multiplication of those weight after being quantized, and look at this, so you can see like using the quantized representation, the basic multiplication, it takes like almost 100 times faster than the weight that is not quantized. So we can see like quantization in this sense actually make it easier to do that. But also quantization also also reduce memory storage requirement by a factor by some values. So we can see here we also divide the memory storage before quantization and also quantize. We can see this is 4 times before that. So in an essence, we can see that quantization helps in too many ways, as we can see here. It helps us to speed up our performance and also computational performance, and also the memory footprint is now reduced. The quantization they explain in the book, you can do quantization from different ways. There, what they discuss in the book: dynamic quantization, static quantization, and there is another one, quantization aware. Yeah.
So the example you showed above, you're taking the same distribution, but you're turning it from floating point numbers into integers. Is that basically what's happening in the example above?
This one?
Well, up top, you showed it. You showed how they took the distribution and they turned it from floating point. It's a narrow distribution.
This one?
Yeah, so then above that, keep going up. There you go. That's the result of your quantization. You have a tensor with no floats in it. Well, yeah.
Okay.
Isn't that right? That's your new distribution, the one that has all, I mean, I know they're probably floating point, but they have no decimal places. They all look like integers.
Yeah. You can see here, we just, run them and put them to characters. So that's why they are here. We are not representing them as floating point here. We just,
right, but what is the quantization? Are you reducing the number of places? Are you or are you? Is it just the changing the distribution from such a narrow band?
So the quantization, I think, so for each number, each digit is represented in different kind of, representation. For example, I'm not sure if I get what you mean. So for example, we can represent a digit in different kind of representation. For example, 8-bit, 16-bit, 32-bit, you know what I mean? So for 32 bits representation, we can represent number in 32-bit, but the 32-bit representation takes much space, and those space is actually for deep learning, for the weight, they don't actually occupy that kind of large space that we use 32-bit. So using 32 bits to represent weight and activation function, we are just wasting much space. So that
right, but we're also changing the scale of the distribution.
Yeah, exactly. Yes.
And we're doing that because you don't have as much precision when you reduce the bits. And so you need the scale to be, stretched out.
Yeah.
Okay.
So that's correct. So anyone want to add something on top of Darius?
I had a question. One of the distributions show that there are some missing values. I don't know if it's obvious to see why they're missing. Not this one, but I think one of that one. It shows that when you're doing quantizations, like some values are missing because I don't know if it's part of rounding or.
Yeah. Okay. I'm not sure actually. Okay. So I think, so maybe if, for example, we are, the bits represented in 32 bits representations, and now we are, bringing this down to 8-bit representation. I think naturally we may have some weights. Maybe they may be outside the scope that can be represented in this 8-bit. I'm not sure anyway. So that we may miss those. I'm not sure. But maybe somebody can chime in if Yeah,
it is actually the fact that when you map the full range and precision of values that can be represented by, let's say, 32 bits of floating point represented values, and you discretize them to the values that can be represented by 8-bit integers. Remember, 8-bit unsigned can only represent 256 values, and signed is also close to that. So then you have only that many precise values, and any other value so only a certain number of the total values that you represent by, let's say, floating point 32 bits can precisely map exactly to what the 256-bit integers represent. Every other value which doesn't precisely map will have to be rounded in order to fit, or it will be snapped to the closest matching integer value. And therefore, there are values in the totality of the floating point 32 which are not exactly mapped, and all those values will be imprecise. That's why, for example, if you go back from the 8-bit integer to try and represent the original floating point 32-bit value, you will not get exactly the same value. You will get a different value because you're rounding and snapping to the 8-bit integer, which is not precise. So a lot of values from the floating point 32 values will snap to the same value of 8-bit integer. So when you go back, you will get errors. That's the source of the errors for the inaccuracy.
Okay, good question. I'm not sure, Silvina, if you may know why do we assign, what's the point of assigning while 0 equal 0 point?
Yeah, so there are two ways that you can actually map the floating point values to the integer values. If you, first of all, assume that the integer values are signed integer, so signed 8-bit, so it's from -128 to +127. But the first bit is a signed bit, and then the rest of the bits. So you have 1 bit of sign and 7 bits of actual values. So it goes from -128 when the first bit is 1 to +127 when the first bit is 0. Now, and therefore we're representing or quantizing using signed 8 bits. Now, in that case, or generally in any case, you can actually quantize in two ways. You can do affine quantization, and affine means, a scale and a 0 point. So S times, according to the equations, S is what you use to map the range, and then you also assign it a 0 point. Now, when you do, so that is affine quantization, and when the 0 point is mapped, the 0 point is the 0 value in any range. So for the floating point value of 0, it's between minus, whatever the floating point 32 values are. If that's exactly mapped to the 0 in the quantization range, then you have a symmetric mapping of the range, right? Between the 0 point of the FP32 and the 0 point of the quantized int 8, signed integer 8 are exactly the same. And if that's the case, then you have a symmetric mapping, which means that you have the negative -128 and the positive 127. It becomes -127 to +127, and the 0 points exactly align. And that is typically known as just scaled mapping. And what he has shown here is scaled mapping, which is why you make the 0.0, which means the 0 of the floating point 32 value and the 0 of the integer 8 values map to each other, right?
Okay.
You can have a case where the 0 of the floating point 32 values doesn't map to the 0 of the integer 8 values. That's also an acceptable mapping, in which case the mapping of the values will not be symmetric around 0. But if you do that, if you do the non-symmetric mapping, then you get into problems with the 0 values and stuff, and you have to adjust in the arithmetic. So in order to avoid all that complication, they do the scaled mapping, which is the 0 of the floating point is made to map to the 0 of the int. And the values then in the quantized range are symmetric around 0.
Okay, cool. So what also I think I didn't know from the book is like so here, what about, so the for example, I think our model bad base they are 32-bit. Now trying to basically do quantization using 8-bit. So does that mean like if we now do quantization using 16-bit, the 8-bit will have less storage than 16-bit, right? 16-bit. So is there any like anybody knows what is maybe in the literature the preparable quantize? Can we quantize to a 16 that we may not lose much accuracy than quantizing?
Yeah. So today the state of the art, and again I have to be careful when I say today because I'll tell you two things: as of today and as of yesterday. The reason I say it that way, I'll explain in a minute. But first, until very recently, BF, what is called as brain float 16, which Google originally came up with,
yes,
which is in the 16-bit. Now from 32-bit, but let's start with 32-bit and then I'll take you to the remaining steps. So in 32-bit, you have one sign bit, and you typically have 23 what are called mantissa bits, which is the bits that you use to calculate the value after the floating point. And then you have 8 exponent bits. The exponent is what gives you how much do you raise the value to. So the exponent is, 2 to the power of whatever the exponent bits are. So there are 8 exponent bits, 23 mantissa bits, and 1 sign bit. So when you add them, you get 32. Now, originally, when they did FP16, then they actually just used and simplified it as 1 sign bit, 5 exponent bits, and 10 mantissa bits. Now, what you will notice when I say that is the number of exponent bits in the 16-bit, in this FP16 version of how they allocate the bits is 5, whereas the original floating point 32 bits had 8, right? And therefore, the range of values that the FP16 could support was smaller. So, in the chart that you see above, if you scroll up a little bit, the division chart that they show on the number line, the range is limited for FP16 compared to FP32. Some time back, Google came up with this mapping thing called BF16 or called BrainFloat 16. And the difference between FP16 and BrainFloat 16 is the fact that they allocate the exponent and mantissa bits differently. So what they do in BrainFloat 16 is its sign bit is 1, but the exponent bits, the bits that are allocated for the exponent is 8, which is the same as for FP32. And then they reduce the number of mantissa bits to, you're now left, if you add 8 plus 1, you're 9. So of the 16 bits, you're left with only 7 bits. So BF16 is a sign bit of 1, exponent bit of 8, exponent bits 8, and mantissa bits of 7. So you have 16 bits. What advantage does BrainFloat 16 give you compared to FP16 and with respect to floating point 32 is the range of numbers you can represent with BF16 is the same as the range that you have with FP32. Okay, because you use the same number of exponent bits. Now, the only difference then becomes, and that's why if you scroll up, I'll explain also what the chart means. Not down, up, further up. Yeah, hold there. So what in BF16, for example, or floating point 32, the Qmin and the Qmax, which shows you the range, are exactly the same because the number of exponent bits are the same. What differs is the distance between these notch marks on the line, because the notch marks on the line shows you how many buckets you have, and that's the mantissa bits. And the mantissa bits in case of FP32 are a lot more. There are 23 mantissa bits, whereas in case of BF16, you have only 7 mantissa bits. So the range is the same, but the number of slices that the range is chopped into is a lot coarser in case of BF16 or even FP16. Okay, so that's what this diagram is indicating. You can see that, and of course they have shown it for integer, that the number of slices that you cut the range into is reduced in case of integer, and it is reduced in case of FP16, it's reduced in case of BF16 too, right? So I think even today, the training is done in BF16 for most of the cases because you do not lose much precision by doing it in BrainFloat 16, because again, as I explained, the range is the same, it's only that the number of buckets are smaller. So you don't lose much precision. And the reason they also do that is because it's very easy to translate numbers from FP32 to BF16 because the exponent remains the same. It's only the mantissa that you have to modulate. So training is typically done in BF16 and inference is what is done until very recently in int8. But just about a week ago, or maybe 2 weeks by now, a bunch of hardware companies, Intel, NVIDIA, Qualcomm, and so on, came up with something called FP8. And there are two versions of FP8. I won't bore you with those details, but basically FP8 says you can actually use 8-bit, not integer, but even 8-bit floating points in order to represent the values. And they kind of, there are, the white paper that these companies published illustrates that you can pretty much get back all of the accuracy that you would wish to have, even for very large models like transformer models, up to 175 billion parameters and stuff, using FP8. But that's, it's even the format has just been announced 2 weeks back. So the hardware to support it and stuff like that in the hardware will probably take, I don't know, next generation of, the processors and things to support that. But when that happens, I think everybody will again switch to FP8 for inference. But today's state of the art is BF16 for training and int8 for inference.
Okay, right. So thank you for that information. Okay. Okay, so I think we stopped here where we says the quantization they made. They explain different kind of quantization, dynamic, static, and quantization aware. But I think they said the dynamic, I think, is widely used. So here, this is how we can, train our model using quantized dynamic. We can see here that we put our model and now we change this to a quantized model. And now here we are benchmarking the performance with the quantized model. And now we can see this is the, benchmarking. We can see here that distillation with quantization, we can see this is it, right? We can see now we add distillation and quantization. We can see like we reduce a lot of latency and even, the performance we can see increase. So this means that I think in the beginning of the chapter, they explained that I think in the beginning, So I think this is Roblex engineering. What they had performance was this. They had the distillation and quantization, which achieve a greater, latency and also the throughput. This is the best settings they have. So that's so that's what we have here as well. We can see the distillation and quantization actually had a good performance. So they said, let's see if we can push the our optimization to the limit. So can we do much better rather than these guys? It turns out that there is something they presented, which is ONNX, which is a framework that can be used, to represent deep learning using some kind of graph. And it makes easy to switch between, model train in one format to another. For example, also you can train your machine learning, you can train in Python and deploy in other languages. And they show us this kind of runtime environment. Unfortunately, I tried to run this. I think it's still not, I saw the Catalan and Srivinas. I saw your issue in GitHub. I went there, but this is not yet. I think. Does anybody of you try to see this is solved or not yet? because the code is not working from the book, also from the GitHub is not working.
Yep.
Yeah.
This isn't solved yet.
Okay. So what I have just from the book, just let's see, the performance. They do the distillation from with what do you call it? ORT, which is the optimized ONNX runtime. And we can see just to show the performance here, we can see this is the distillation from ORT. I think this is the one here. And we can see that the latency is somehow much better than this one, distillation and distillbat, and also base, but the latency is much better. But distillation and quantization, this is distillation and quantization, I think the latency is much better. So can we also do much better by adding the distillation from with ORT and quantization to put all this stuff so we can see the performance here? So it means that the latency increased. In fact, I'm not sure if the accuracy also increased. So the main idea, I think, because I was not able to run this code, just this figure, it means that we can basically use this ORT plus distillation and quantize. It gives a better performance than using only distillation and ORT. I'm not sure if anybody can add something because this code is not working from the book. Anyone wants to add something? So these approaches we saw, the distillation and quantization and these ONNX are basically used to speed up our performance of our model in smaller stuff. But one way to reduce the weight of our model is what is called pruning, weight pruning. So this is the last part of the book. They discuss about weight pruning. I think the main idea we are still trying to see. So distillation, quantization, and ONS, I think we can see like we improve the latency and also the accuracy, but also we also interested also the weight as well to decrease the weight. So weight pruning basically is a way in which we remove some weights that are not actually they have least important in the network. So we can see here, this is from the book before pruning, and this is after pruning, and they can reduce basically the memory footprints. They have also different kind of pruning. One of the ways they talk about is weight pruning, which basically is used to calculate or a matrix of importance of those weight, and now select the top key percent of those importance. So given this kind of weight, they calculate the matrix and now select the top ones. So they have also called movement pruning, which they said it was proposed by guys from Hugging Face. I don't know how far the approach has gone now. Right. So that's, I think, the end of the book. But anyone wants to add something? Yeah.
Yeah, the couple of things I'd comment on is, they, at least in my opinion, they kind of don't do a very good job of explaining quantization and the various methods that are used. And it turns out that if you dig into it, at least part of the reason they just show you dynamic quantization is because it turns out that Hugging Face models, they haven't yet provided good API or support for quantization for what is called the second method of static or post-training quantization. And outside of Hugging Face models, I believe, from whatever little poking around I could do, that it's actually the case, and you can see that in the FP8 paper and stuff, that outside of this limitation that Hugging Face transformer models have, it's actually the case that post-training quantization, or what is called PTQ, which is referred to as static quantization, where you quantize both the weights and the activations, and you do it by sampling the activations and not doing it dynamically, but statically. That turns out to provide, in most cases, better accuracy for your models than does dynamic quantization. So even though they say, oh, transformer models, typically you use dynamic quantization, that's not actually true in general. It's only because it's a Hugging Face model that its simplest thing to do is to do dynamic. But if typically you want more accuracy, which you do, then it's better to use post-training quantization. And if even that doesn't give you the accuracy that you want, or the reduction in size that you need, for example, in mobile or IoT type deployments, then you go to quantization-aware training, which is the third approach they mentioned. So it's not true generically for transformers that dynamic quantization is the best approach. It's true only because Hugging Face has some limitations.
Okay, I see.
As of right now, to use the transformer models in Hugging Face and do post-training quantization. So outside of that, I think many of these big companies do post-training quantization or quantization-aware training.
Okay, cool. I've also seen like one book that I think is good for this, like called TinyML, which is basically like all these. I started reading about this quantization, about model compression, which is also a good read. I quite agree, like they didn't discuss much about the quantization in the book. They only talk about the dynamic. So yeah, so this is the last bit of the book. We have the next chapter, which is gonna be, what is the next chapter? Fine-tune few to no levels. So anyone want to add something now before we go? Okay. I think the next chapter, few to no level, chapter 9, we still don't have anyone sign up. If anyone is interested, please do sign up before next week. Right. So I think if there is nothing that we can discuss, then we can see next week. Darren?
Yeah.
You want to add something?
No, I got nothing.
Okay. Right. So yeah, so thank you all for coming today. Today is just basically the last part of our last week's session, and yeah, we have seen it, and I think we have, as I said, chapter 9, few to no levels. If you are interested for the presenting the chapter, sign up, and we see next week. Thank you all, and thank you all for contributing for the sessions, Steadiness and the other. See you next week.
Thanks. Bye.
Bye.
Thank you. Bye.